Welcome everybody to this thematic meeting about crop management, focusing on nitrogen management. My name's Peter Berry. I'm based in the UK and I work for a company called ADAS. I'm a crop scientist. Can I ask everybody, if you haven't already, to mute your microphones, please? And I will introduce you to my co-presenters as and when they start to present. So the aim of our meeting is to provide an overview of the agronomic factors that farmers and farm advisors need to be aware of to minimise greenhouse gas emissions associated with nitrogen application to crops. And importantly, we want to achieve this whilst at least maintaining our crop productivity. So it's a real challenge. We have a number of experts with us to help give the background to this. This is our agenda. We'll start with an introduction, which I'm going through at the moment, and then we'll summarise where we got to in our last thematic meeting about crop management, summarising the effect of different sources of greenhouse gas emissions. And then we'll focus on the yield and quality response to nitrogen fertiliser. And then we'll get to the meat of the webinar, where we'll discuss approaches for reducing greenhouse gas emissions from nutrient applications. I should mention that I've recorded this webinar so that you've got access to it and can use it in the future if you want to. And no doubt you'll have questions, and we do encourage questions. So if you have a question, then what I suggest you do is click on this chat button and then write your question in the chat, and either myself or the other co-presenters will answer that question during the meeting. We've also got time towards the end of the meeting for discussion as well. So but I certainly encourage you to put those questions in the chat during the meeting so that everyone else can see the questions and we can get them answered during the meeting. Okay, so I wanted to start the meeting with a poll to really understand how you or the farmers that you advise currently manage nitrogen to be able to minimise greenhouse gas emissions. So in your screen, hopefully you'll see a list of questions come up which we'd like you to answer. Please do that and we'll see the results of the poll coming up shortly. Okay, so we can see the results coming in here. What approaches do you use or advise to minimise synthetic nitrogen fertiliser use? You can see it's fairly even, but the greatest responses are coming in to create a nutrient plan at 23% at the moment. The use of cover crops not far behind at 21%. Yeah, if you could mute all your microphones, please, that would be brilliant. And then we've got the use of nitrogen fixing crops coming in third there. Still see a few results coming in, so I'll just pause for a few more seconds. Okay, so that's interesting to see. There's not only 4% using nitrogen efficiency additives such as urease inhibitors and nitrification inhibitors, so that's informative for us as well. But the most common ones are a nutrient plan, cover crops, and nitrogen fixing crops. Okay, Thanks for posting that, Ben. Ben, if I ask you to share your slides now. Ben is a colleague of mine. He's going to give the background to the general sources of greenhouse gas emissions associated with growing crops, really just to get us onto the same page and to kick on from the last meeting that we had where we summarised and went into more detail on this. So thank you, Ben. Over to you.
Thank you, Pete. Yeah, thanks everyone. I'm Ben Haig. I work with Pete at ADAS here in the UK. And today we're going to be talking about the carbon emissions associated with nitrogen from synthetic fertiliser and organic materials. And this will be based on our YEN-Zero service. So this is where we've surveyed several hundred farms and fields. And this was to try and establish the carbon emissions associated with these farms and fields. And we'll be discussing the headline results here in this meeting. So firstly, a couple definitions. We're going to be talking about carbon emissions, and this relates to the equivalent warming effect of carbon dioxide, nitrous oxide, and methane described in terms of carbon dioxide equivalent. And we could also be talking about greenhouse gases, which similarly also refers to carbon emissions, as does carbon footprint. And so today we're talking about crop production, and the main two key greenhouse gases in crop production are carbon dioxide and nitrous oxide. We're also aware that methane is a significant greenhouse gas in agriculture, but this is more to do with livestock production, whereas today we're going to be concentrating on crop production. And we're also going to be talking in terms of crop carbon emissions, and we will be using carbon dioxide equivalents to allow us to compare between CO2 and nitrous oxide emissions. This is important because nitrous oxide has a warming impact of almost 300 times that of carbon dioxide. So it's really critical that we try and think in terms of carbon equivalents so we can reduce our N2O emissions. And we can do this relatively easy with good nutrient management. So this is a big lever for crop production moving towards net zero. So in our YEN-Zero database, we split carbon emissions into 8 categories, which fall under 3 main divisions. So firstly, we have our embedded emissions. So these are brought onto the farm in the form of manufacture of our inputs. So these are seed inputs, ag chemical manufacturing, nitrogen fertilizer manufacturers, and also non-fertilizer manufacturers. And then we also have energy carbon emissions. So these are mainly to do with fuel and electricity. So this is mainly diesel consumption in machinery, but also energy required to dry grain and store crops, such as a potato cool storage. And lastly, we have the direct and indirect nitrous oxide emissions. So these are mainly associated with nitrogen fertilizer application, organic amendment application, and also crop residue decay. When we say crop residue decay, we refer to when residues are left on field and the residue material breaks down and decays, which releases nitrogen into the soil and interacts with the nitrogen cycle to form nitrous oxide after harvest. And a key driver of these emissions is the amount of nitrogen available in the soil and also the soil moisture and temperature. So moving on to how we calculate the carbon footprint of different sources. So here's one example, which is our fertilizer. So for some fertilizers, we have independently accredited carbon footprints. A couple examples here are CF fertilizers and also Origin fertilizers. And for these fertilizers, we have established carbon footprints for how they were manufactured. And we calculate 28% of our fertilizer in this way. And the remaining fertilizer, we get a carbon footprint from the peer-reviewed literature. So one example here is Brentrup et al. 2018. And this paper gives us an emission factor, so we can calculate the carbon footprint of applying different fertilizers. And we also assume that fertilizers is manufactured within the EU. And it's worth noting within the EU that all fertilizer manufacturers have abatement technology to reduce N2O emissions. So moving on to nitrous oxide emissions, the main sources of nitrous oxide emissions are from direct emissions from the soil following fertilizer application. And this is based on a government report called the UK Greenhouse Gas Inventory, which establish different sources of carbon emissions across different sectors, including agriculture. But there are also other nitrous oxide emissions sources, including indirect emissions from ammonia volatilization following fertilizer application, indirect emissions from nitrate leaching following fertilizer application, and also direct emissions from decomposing crop material left in the field, such as crop residue decay. And there is also a couple other considerations we have to make when determining nitrous oxide emissions. So one example of this is annual rainfall. So we know that nitrous oxide emissions from ammonium nitrate fertilizer is positively correlated with annual rainfall. So the more rainfall, the more nitrous oxide emissions. Similarly, urea has lower direct emissions, but higher indirect emissions via volatilization than ammonium nitrate fertilizer. And also we consider if an inhibitor is used, so inhibitors reduce the emissions. For example, a nitrification inhibitor reduces N2O emissions by 44%, and a urease inhibitor can reduce emissions by 70% and 44%, resulting in indirect volatilization for emissions for urea and urea ammonium nitrate, respectively. So moving on to the distribution of emissions for different crops. So this is not an example of how much emissions are from this crop, but where the emissions are distributed within the production of a winter wheat, feed wheat. And the headline figure here is that over half the emissions are associated with nitrogen fertilizers. And this is the manufacture of the fertilizer and also the application, resulting in nitrous oxide emissions. So you can see the dark blue and yellow segments here represent the nitrogen fertilizer, and this accounts for over half the carbon footprint of a winter wheat crop. And a couple of other important figures are the 17% from fuel and electricity. So this will be diesel and also energy, and also 13% from crop residues. So this is crop residue decay following harvest. And it's worth noting that just 1% of emissions come from ag chemicals. So this is crop protection products. There is a bit of a assumption that crop protection products make up a greater proportion of carbon emissions, but this is not the case. And here is an example for an oilseed rape crop. So similarly, we see that nitrogen fertilizer make up the overall bulk of the carbon emissions for this crop, making up just under 50%. Whereas the main difference between winter wheat and oilseed rape is that oilseed rape has a greater proportion of crop residue decay. This is because oilseed rape has greater nitrogen content in the store, which means that there's greater emissions in terms of nitrous oxide following crop residue decay. And lastly, we have a diagram of a bean crop. So a bean crop's quite different because they are nitrogen fixing, so they don't have any nitrogen applied to the crop, which means that the distribution of carbon emissions is mainly associated with fuel and electricity and also crop residues. And this just illustrates how we need to consider different ways of reducing emissions depending on which crop we are growing. So lastly, the key take-home messages are that pulses have a lower carbon footprint compared to cereals, and this is between 600 and 800 kilograms of carbon dioxide per hectare. And then we move on to low input cereals, which have such as spring barley, which have a carbon footprint between 1,500 and 2,000 kilograms of carbon dioxide per hectare. And lastly, high-end input cereals and also oilseed rape. So these are things like milling wheats, which have the highest carbon footprint between 2,200 and 2,800 kilograms of carbon dioxide per hectare. And to summarize the different carbon emission sources for each crop, so for cereals and oilseed rape, the main form of greenhouse gas emissions are from nitrogen fertilizer, making up between 40 and 50%. The next is manure application, making up 15%. Operation, so our energy and fuel costs, between 30 and 20%. And lastly, residue decomposition, which can be between 12 and 24%. And then for pulses, most of the carbon cost comes from the operations, so this is 43%. And then secondly, 33% from crop residues. And lastly, it's worth noting that we can see a threefold range of carbon intensity for individual crops within each crop species. So this suggests that there is quite a large scope to reduce emissions depending on how we manage our crops.
Thanks, Ben. That's great. I reiterate, if you've got any questions, put them in the chat. I can see a few going in already. You'll notice that Ben purposely didn't mention the nitrous oxide emissions associated with organic materials. That's obviously a big part, and our colleague Federico is going to describe that in more detail a bit later on. What Ben described was a description of UK crop production and the greenhouse gas emissions associated with producing UK crops. It's going to be different in different countries, but you can see the general picture there that synthetic nitrogen fertilizer accounts for about half of the greenhouse gas emissions for non-leguminous crops. So you can see the importance of getting that nitrogen management as good as possible for those crops. So what we're going to do next is just summarize the response that crops have to nitrogen fertilizer for different crop types and for different regions within Europe. So myself and a number of colleagues within the Climate Farm Demo project will go through this. And again, if you've got any questions, please put them in the chat. So next slide, please, Ben. So I'm going to start just by describing a general response that crop yield has to the increase in nitrogen fertilizer. It's a generic response that you can see here. The x-axis describes the increase in nitrogen supply, either firstly from the soil and latterly from synthetic fertilizer or nitrogen from organic materials. And then the y-axis, the vertical axis, describes the crop yield. And you can see that the initial increase in yield comes from nitrogen supplied from the soil, and that takes you up to maybe 2 to 5 tons per hectare for a cereal crop, for example, and that brings you up to position A on that graph. And then after that, you need to apply nitrogen fertilizer often to bring the yield up to the potential for the crop. So that brings you up from position A to position B, and that's the economic optimum nitrogen rate. It's often just below the maximum yield possible because of the law of diminishing returns, that each extra kilogram of nitrogen fertilizer gives you less and less back in terms of yield, to the point where it's not really economically justifiable to add another kilogram of nitrogen because you don't pay for it in terms of the extra yield. So that's the economic optimum N rate. That's position B. That's really where we're aiming for here. I think that's the critical point. We're really not trying to get to C, because that would be an excessive amount of nitrogen. It would be unprofitable anyway, and it would significantly increase greenhouse gas emissions. So we're really trying to work out how we can get all our fertilization close to the economic optimum B. Next slide, please, Ben. So this is just some real data. This is for wheat, and you can see that the increase in nitrogen fertilizer applied on the x-axis there increases the yield from about 5 tons per hectare without any fertilizer to just over 10 tons per hectare with fertilizer. And the economic optimum for this particular crop was just under 200 kilograms of nitrogen per hectare, and that's typical for wheat crops grown in the UK. Next slide, please, Ben. And then this graph shows the impact of nitrogen fertilization on the greenhouse gas emissions. So the black line there is very similar to the yield response that you saw in the previous graph. It shows how yield increases with increasing fertilizer, and you got the yield there on the second vertical axis on the right hand side there. So that's the black line. And then the shaded areas at the bottom of the graph are the greenhouse gas emissions per ton of wheat produced. Now you can see that at the economic optimum N rate of about 200 kilograms of N per hectare, the greenhouse gas emissions are about 400 kilograms of CO2 per ton of wheat produced. But we could minimize that by actually not applying any nitrogen fertilizer, and you'd move to the left of that graph. And actually, the optimum fertilizer rate to minimize greenhouse gas emissions per tonne of yield is just under 50 kilograms of N per hectare. But you can see what would happen if you did that. You'd actually get a much lower yield. So the yield at that sort of nitrogen rate would be around 6 to 7 tonnes per hectare. And you can see that's going to be a big reduction in the yield. We need to think what the implications of that might be. It would probably be to expand the cropping area, and that would have all the implications of that in terms of biodiversity and just the additional area of land which is farmed. So, I think the real emphasis of today is that we want to find ways of fertilizing our crops at the economic optimum N rate. That will maximize our profit. It will maximize the yield in terms of the amount of nitrogen used, and it will minimize excessive greenhouse gas emissions from overuse of nitrogen. So that's really the objective of the day. And you'll see as we move through the day, we will be looking at ways of how we can better predict the optimum N rate and make more efficient use of the synthetic fertilizer and the organic materials to help us to get to that point by applying as little nitrogen as possible. Next slide, please. Thank you. And we're going to move on to Francis now, who's going to describe some yield responses for crops grown in France. Over to you, Francis.
Thank you, Pete. Good morning, everyone. I'm Francis Flenet. I'm an agronomist at Terrinovia, which is the French Technical Institute for oilseed crops and for grain legumes. And at Terrinovia, we conducted almost 70 experiments to optimize nitrogen fertilization of winter oilseed rape. And this slide presents some of the results we got. This figure shows the response of seed yield to the amount of nitrogen applied. And these results are the mean results. You can see the typical response of seed yield to nitrogen rates, but of course, in some of the experiments, the response could be quite different. But on average, that was the response. We calculated the technical optimum of the amount of nitrogen. We defined this optimum as the nitrogen amount to reach the maximum yield minus 0.1 ton per hectare, because above this value, the nitrogen use efficiency is very poor. In this figure, you can also see the effect on seed yield of 20, 40, 60, or 80 less nitrogen than the technical optimum. We also calculated with a decision support system called Reglet Azot Colza the amount of nitrogen to be applied in each of these experiments. And you can see that on average, the amount of calculated nitrogen was 15 kilo higher than the technical optimum. You can also see in this figure the economic optimum. This optimum depending on rapeseed price and also on nitrogen price. Next slide, please. We used all these results for an economic evaluation of the DSS Reglet Azot Colza. And in this table, you can see the differences between the economic optimum calculated in the experiments and the nitrogen rate calculated with the DSS Reglet Azot Colza for different prices, for the prices in 2020, in 2021, and in 2022. The DSS slightly overestimated the nitrogen rate needed to achieve the economic optimum. With the prices in 2021, the difference was almost zero. And the difference between the two nitrogen amounts was maximum in 2022 with high rapeseed prices and also high fertilizer prices. Next slide, please. We also use the database to calculate nitrogen use efficiency, which is the seed yield per kilo of fertilizer nitrogen. This table shows the effect of the application of 20 kilo of nitrogen from 80 kilo less than the technical optimum to the technical optimum. The nitrogen use efficiency decreased the closer you got to the technical optimum. It means that at the technical optimum, we had a low nitrogen use efficiency. And we also got a low nitrogen use efficiency at the economic optimum, because the economic optimum was even greater on average than the technical optimum. Next slide, please. In these figures, I plotted the difference in seed oil content and the difference in seed protein content against the difference between the nitrogen applied and the technical optimum. The seed oil content decreased as the difference between nitrogen applied and the technical optimum increased, and that was the contrary for the protein content. It means that seed oil content and protein content were negatively correlated. For this reason, seed quality is not a factor when we calculate nitrogen rates, because oil and protein are both valuable. Next slide, please. In summary, we can say that the amount of nitrogen fertilizer calculated with the DSS Reglet Azote Colza was close to the economic optimum. There was only an overestimation of 5 to 20 kilo of nitrogen per hectare. One shouldn't apply more nitrogen than the calculated dose in order to avoid loss of money, nitrogen waste, nitrogen pollution, and increased greenhouse gas emissions. Unfortunately, in France, in 2015, there was a 27 kilo nitrogen per hectare over-fertilization of winter oilseed rape compared to Reglet Azote Colza. And it's still the case, so there is still a room for improvement. More improvement is possible. More improvement of the nitrogen use efficiency and hence of the greenhouse gas efficiency is possible by applying less nitrogen than the rates calculated by Reglet Azote Colza. But it would have a cost if the reduction is above 5 to 20 kilo of nitrogen per hectare. Thank you for your attention.
Brilliant. Thank you, Francis. I'm going to ask Ben to stop sharing and ask Sven to share his slides now. And Sven's going to talk a bit about yield responses to nitrogen in the Nordic region. Okay. Over to you, Sven. Thank you.
Thank you. Is everything working? Do you see my slide and you hear what I'm saying?
I hear you, and I can see your slide well. Thank you.
Okay. Well, hello, everybody. I was given this headline to talk about N fertilizing in a group of crops in our region, and our region is Denmark, which is a small piece of land sitting on top of Germany, as many of you know. I work in an organic innovation center, so my approach will be organic. But I think what I've chosen to show you is applicable or could be interesting for almost any farmer. I think. Let's see the sharing here. There it is. We've done a lot of trials in how to fertilize the organic cereals cropping, and one of the big issues in organic farming is how to utilize the limited amount of nitrogen available. And the figures I showed you here is a series of trials where you test different pre-crops, and the green line is a pre-crop grower grass. That means a crop that's been 2 or more years lying as for harvesting grass clover for feeding cows. And the blue lines in the figures is the same crop grown with a pre-crop of other crops than grass clover. And it's quite obvious that to the right you have the spring crops, the oats, the barley, and the spring wheat. It's quite obvious that the response for applied fertilizer, that's from 0 to 200 kilos of ammonium fertilizer per hectare applied, is that the response after a pre-crop of grass clover is very limited or even zero. There's a small reaction in the spring wheat application. If you have a weak pre-crop like other cereal crops, then you can see the natural and well-known response. To many organic farmers, and I have not in this presentation time to dig more into the data, but I can see many farmers, when I go into the data, they don't utilize the pre-crop grass clover with quite trust. So they apply, some of the organic farmers apply quite a lot of nutrients or nitrogen to even after plowing the grass clover. That's a decision I would like to discuss in the next few slides. Looking at the winter crops, winter rye, winter wheat, and winter triticale, which used to be a quite interesting crop for organic farmers. Now it's been taken out by yellow rust. But the winter crops, they respond a lot better to nitrogen applications even after grass clover. But the gradient on the curve is more the same. So the value of each kilo of nitrogen applied on the winter crops is more or less the same, independent of what pre-crop you have. So the consideration to take from this is that you need to consider where to use your nitrogen, because in an organic system, nitrogen is a limiting factor in most places anyway. So you have to look at where can you find the best value. We've done a lot of trials in this, and this new figure here is more or less the same as the barley on the other side, and we tried different organic fertilizers that we can use in organic farming. We have the slurry, we have the digested household waste, and we have some mixtures of these, and even some fertilizer, the yellow dots. That's fertilizer made of meat and bone meal, 100% organic nitrogen. So you can see they all react and to the same response more or less. So all these organic fertilizers, they behave in more or less in the same way, looking at this barley experiments. And we have done this kind of experiment many times over the years. So it's a very well-known response curve. Looking at, where is it? I changed it. Something wrong with the... That is, looking at winter wheat. I have taken some conventional winter wheat trials, and they're quite old now, from 2002. And the line, the brown line is the gradient of crop yield. That's an index of from 0 to 120. So it's not yield, it's not kilo yields, but it's the index. So if you grade the winter wheat crops after increasing yields, and then you can see the protein content, the crude protein content, the green dots is quite scattered. If you dare to make a sort of to draw a line and to see where it points, you can see the expected development, that you have an increase in yield, you have a decrease in protein content. That's very in many other situations that are very well established. If we look into some of the organic trials we did same years, they're quite similar, but they're quite even quite significant. Because looking at the spring wheat baking varieties, this is 15 different varieties. Some of them are at the time modern varieties, bred for bread baking, for baking varieties, and some of them are taken out of gene banks, very old varieties with old abilities to produce straw and yield, so on. So if you grade the crop yield after they're fertilized, and it's fertilized with about 70 kilograms of ammonium nitrogen. Then you see the yield is going from around 35 to up to 50 something, and that's 3 to 5 tons per hectare. Quite really good yields. It was a good year and good crops and good soil conditions. And then you can see the red columns, they are unfertilized. So it is quite fertile soils. But you can see the gradient from the crude protein content is going from almost 15, I think 14.7 is the highest one, to around 10-11% of protein. And looking at that, and looking at one of the comments in the chat before, is that if you choose the right variety, you can produce a good quality milling or baking spring wheat on almost any kind of nitrogen input. And then it's a discussion: do you want to produce feed for pigs or food for people? Depending on what you choose, you can feed a lot of people by this choosing the variety that make the best quality, even when nitrogen application is one of the major limiting factors as it is in organic farming. Then back to some very to how we could work this in the advisory business. This is more or less the same thing. You have this response curve. You have 4 crops here: the barley, the winter rye here, and the rapeseed, and the ryegrass for seeds, which are quite big crops in Danish farming. And then you can see how much kilos of crop or seed you get from 1 kilo of nitrogen in different intervals from 0 to 50 and so on. And the green markings I've made in this table is the basic recommendation how to reach the optimum. And it's in organic farming, it's around between 15 and 100, maybe close to 100 kilos of utilized nitrogen in the cereal crops, and a little bit higher in the rapeseed and ryegrass. But this is only the agronomical optimum. You want to look at the financial optimum, because organic farmers, they try to make a living as any other farmers. And this, of course, is a snapshot of a situation. I have translated it into euros. We have our own currency still, but it's based on the crop prices at a certain year. So when you make your decision how to utilize or how to use or how to distribute the nitrogen you have available, then you have to look at what is the price of the crop. And you can see the barley crop would pay a fairly good price in the optimum, about 4.7 euros per kilo of nitrogen applied. And the winter rye is the price of rye is a little bit lower, and the response curve is a little bit flatter. So you get a significantly lower price per kilo of nitrogen. And if you go above 100 kilos, you still get a price, but it's quite low. The rapeseed has the optimum around 150 kilos of nitrogen applied with basic wood price. After that, prices goes down. And even looking at the ryegrass, which is a very important cash crop, it's very important that you reach the optimum. If you go below the optimum, you lose a lot of income. And of course, if you go over the optimum, you get a heavy crop that is with poor pollination, and you get you can get losses. This is very basic in many situations, but I can see you are looking at digging into the figures that we use a lot of nitrogen in places where the pre-crop and the system you work in as an organic farmer actually could do a lot to supply the crop on its own. And looking about, as Pete was talking about, the greenhouse gas optimum, of course, we work at quite low application rates of nitrogen, and looking about from 60, 70, 80 to maybe 100 kilos of nitrogen. But we still have to consider, and that we are looking really a lot into that. What are the greenhouse gas emissions from destroying and mobilizing the nitrogen from a grass clover crop? That's a quite big issue, because you you can apply, or you activate a lot of nitrogen, maybe 200 to 250 kilos of nitrogen, and we have to know about what does that go, considering how to looking at the greenhouse gases. But this kind of optimization is really basic and it's really important, and it's not done as much as it could be when the advisors are working with the farmers in the planning. I think that was all from me.
Thank you, Sven. A really good example of the importance of the previous crop on how much fertilizer or nitrogen is required for following crops there. That's brilliant data. We're going to move on to glasshouse crops now. I'm going to ask Miguel to share his slides and just briefly introduce himself. Thank you. That's good, Miguel. We can see that slide.
And I think you can hear me now.
Yes.
Hi, I'm Miguel Jimenez. I am an agronomist. I work for Coexpal. Coexpal is an association of producers of fruits and vegetables in southern Spain. We have a technology innovation center, and our main duty is to transfer knowledge to the technical departments of our associates, which are mostly agricultural cooperatives, and also to farmers. Our main production system in the area are greenhouses, but these are kind of low technology greenhouses, passive greenhouses in which the use of energy is very low. So in terms of the emission of greenhouse gases, the major source are fertilizers. So that's why we're trying to optimize to give information and to give knowledge to our growers to improve their efficiency in the use of fertilizers. My presentation is going to be very short. I'm going to discuss a few ideas on how nitrogen management has evolved in the last decades in the area, and some results on the effect of different nitrogen strategies, supply strategies, and nitrogen dosages have on yield, right? So decades ago, the strategy to decide how much nitrogen to supply to crops was based on extractions. So there were a few standard recipes, and you can see one example here for a tomato crop. So depending on the phenological stage of the crop, different amounts of fertilizers were recommended to be applied by the growers. But in time, most of the growers, they adopted, they started to use automatic fertigation systems, which originally were brought here by the Dutch technology suppliers, right? So instead of providing these amounts of nutrient elements to the crops, the whole mindset changed, and the idea was to establish an optimum ionic equilibrium in the root environment to allow maximum absorption of the different elements. So as an example here, you can see the Stainer solution, which was widely used in soilless crops years ago. So this was taken as an initial step that was adapted with experience to the different types of soils and varieties. But this was the idea, to establish a chemical ionic equilibrium within the volume, the soil volume explored by the roots, right? But this was dangerous because the data were not measured. They were just, growers and advisors, they relied on their experience, right? So according to that, the advisors, they decided on the concentrations of fertilizers in the stock solution tanks, and also the pH and the electrical conductivity of the resulting nutrient solution. So the thing is that in the last years we are enforcing advisors and growers to use a different approach, and this different approach is it has been it is known as a prescriptive corrective approach, and the prescription is based on the use of a decision support system to calculate the daily needs of water and fertilizers, and the data needed to have this decision support system run and calculate are the daily temperatures, the humidity and radiation, the soil nitrogen contents and other soil properties such as the texture, the organic matter amendments, how much organic matter has been applied to the soil, the configuration of the irrigation system, and also, as I said before, some soil properties. So this gives the growers and advisors a kind of a general picture of what should be the general strategy during the growing season for the application of irrigation and fertilization. And then this is corrected day by day by some data which should be obtained from the soil, from the plant, and also from the air system, and this is the climate within the greenhouses. So it's generally recommended that growers and advisors should use suction probes to extract the nutrient solution from the soil solution, right, from the root environment, and also conduct some SAP analysis to know if there are any excesses of nutrients or deficiencies in the absorption of nutrients by the crops. Okay, so I'm going to give you now some results by obtained after comparing this comparing a conventional management of the nitrogen application with an improved management based on this prescriptive corrective management, right? So in the red line you can see the accumulated irrigation with a conventional management, and with a blue line the accumulated water applied by using an improved management strategy. So the difference between both systems is 13%, and we don't have to forget that in fertigation, the more water you apply, the more nutrients you apply. So it's very interesting to save as much irrigation water as possible. If the nitrogen concentration in the nutrient solutions applied is compared you can see that the red dots, this nitrogen concentration is much higher than the blue dots, which represent this improved management based on this decision support system. So generally speaking, averagely the nitrogen concentration in a conventional strategy is around 12-13 millimoles per liter, and in an improved management is certainly below 10. So there is a lot of nitrogen which is saved, right? And this is indicated by this graph on the left part of the slide, 38% less nitrogen when this improved management based on calculations and data collected on a daily basis from the crop is adopted, and no difference at all in the obtained yield. So as you can see here, this improved management, despite using less water and much less nitrogen, the commercial harvest was not significantly higher, but a bit above the results from the conventional management. These results have been obtained in a sweet pepper crop. This has been repeated in the most important crops in the area, all of them vegetables. But I'm going to give you some other data obtained in a tomato crop, which is the second largest crop in the area. And this coincides a lot with what Pete explained in the slides that he showed, right? In this graph at the left part of the screen, you can see how the total applied nitrogen expressed in kilograms per hectare affects the total dry matter in tons per hectare of a tomato crop. Maximum is this third treatment here, which is the conventional treatment or conventional concentration of nutrient solutions in the area, which is around, as I said before, 12 millimoles per liter. But if we check how this total applied nitrogen affects the total fresh production of tomatoes in the right graph, we can see that the highest effect, or the most optimal effect, is obtained with this second treatment with a significantly lower amount of nitrogen applied. And this is because when you apply an excess of nitrogen, you have a very strong increase in the leaf area index and also in the vegetative growth of the plants. But in terms of yield, in terms of commercial harvest, it is much more interesting to decrease the concentration of nitrogen in the nutrient solution, so you can be more not only efficient in production from a production perspective, but also from an economical and financial point of view. And
Thank
this
you,
is
Miguel.
all.
That's
all.
excellent.
Thanks a lot.
That's brilliant. Yeah, thank you.
Okay,
Really
thank you.
interesting. Any questions for Miguel, please put them in the chat. Right, I'm going to move on now to the next section of our webinar, which is to focus on approaches for reducing greenhouse gas emissions from nitrogen applications whilst maintaining crop yield and quality. So I'm going to kick off by firstly talking about the importance of nutrient management planning. And really, when you're trying to estimate the nitrogen requirements of a crop, there are three main components to think about. The first one is the demand that the crop has for nitrogen. So we need to consider the expected yield and the concentration of nitrogen within that harvested yield. And then we need to consider how much of that nitrogen demand can be supplied by the soil without any fertilizer being applied. And we need to consider the various processes in the soil, such as mineralization, immobilization, nitrate leaching for that. But generally speaking, the soil will supply quite a lot of the nitrogen that the crop needs. But there is always, or usually, not always, a gap between what the crop demands and what the soil supplies. There's usually a gap. So that gap needs to be met by fertilizer requirement. That can be synthetically produced fertilizer, or it can be organic materials. If you're in an organic system, obviously you haven't got that that facility. You need to rely more on residues from previous crops, for example, and organic materials. But you need to also consider what efficiency the fertilizer that's applied is going to be delivered to the crop. So you need to consider loss pathways such as ammonia emissions or nitrogen which isn't taken up by the crop, is immobilized, for example, to be able to work out exactly how much synthetic or organic material fertilizer to apply. So you can boil down the management plan for estimating nitrogen requirements into this sort of schematic, where you need to consider the crop nitrogen demand, how much nitrogen is going to come from the soil, the efficiency of which the fertilizer is recovered by the crop, and that works out how much fertilizer you actually need to apply. So you can boil that down into this sort of equation here. And SNS is the soil nitrogen supply. In some ways, that's the most important thing, being able to measure that and estimate that using either direct measurements of the soil or lookup tables based on the previous crop and the soil type. So all those things come into calculating your fertilizer management. Okay, I'm going to move on to Federico now, who's going to focus on good management of organic materials. I'll stop sharing and I'll ask Federico to share and introduce himself.
Thank you, Pete. Can you see my screen?
That looks good, Federico. Yes, thank you.
Thank you so much. Then, my name is Federico Dragoni, and I'm a researcher of the Leibniz Institute for Agricultural Engineering and Bioeconomy in Potsdam, Germany. And I'm an agronomist, and at present I currently do research mostly on emissions from the animal production sector. And this is why this morning I'm presenting a few slides on the management of organic materials, especially from the point of view of the greenhouse gas emissions, because as you can all very easily imagine, this is quite important for the livestock systems. So when we talk about the good management of organic fertilizers, in this respect, organic fertilizers are not much different from other fertilizers. The aim is always to maximize the crop or grass growth while minimizing losses to water and to the atmosphere. Maybe to be more precise, I should replace maximize crop and grass growth with maximize the economic outcome of the crop and the grass. So the aim in the end is the same. What is not the same is the complexity of the substrate, because organic fertilizers are typically not a single compound. There are complex mixtures of many components in which the fertilizing components, especially from the point of view of the nitrogen, are sometimes not that concentrated. So the concentration is sometimes pretty low, so that especially the solid fertilizers are rather considered very often soil conditioners than fertilizers, because the prevailing effect is, for instance, on soil structure thanks to the added carbon and organic matter. The advantage is my thinking, as I said, I am at present a livestock system scientist, so my thinking is not that much regarding the case you buy these fertilizers. It's the case that you have animals and you have rather the problem of, sorry for what I'm saying, disposing of such a waste, even if it's not a waste and disposing is not the right term. But in this case, well, for sure, properly using these materials can help you to reduce the fertilizer bill. Although the distribution, the spreading of these materials is not as easy as the distribution of chemical fertilizers, mostly owing to the low nutrient concentration that requires usually the use of heavy and also expensive machinery. And yeah, but on the other hand, these materials can help you address the overall soil fertility deficits thanks to the contents of other nutrients and carbon. And especially in an animal farm, it's something you have to do anyway. So this just to say that unfortunately you cannot expect a too stable composition from these materials. Maybe in your farm under sort of steady management conditions, yes, but there is a high variability among farms. This could be a concern mostly from those importing effluents from other farms. In the end, the guiding parameter is the concentration of dry matter, because these fertilizers are more concentrated or more diluted depending on the content of water and dry solids. And when talking about nitrogen, as I said, it's not a chemical fertilizer, so you have the component that you can consider sort of inorganic, which is usually mostly or entirely ammoniacal nitrogen, but you also have the organic nitrogen embedded in proteins. A few words on the emissions. When we are talking about nitrous oxide emissions from these fertilizers, usually in a simplified approach, these are related to the total concentration of nitrogen. That is literally multiplied by an emission factor. This matters when we deal with a higher level, not the farm level, but for instance the country level. This is how country emissions are inventoried. So the countries have the problem of gathering data of good quality and estimate at country scale the emissions. And this explains why, for instance, the tier 1 approach, which is quite rough, it's a simple product of the applied nitrogen by an emission factor, no matter the quality of the nitrogen, no matter if it's organic or mineral. It is still something that in some countries is done, because the collecting the so-called activity data of sufficient quality is a challenge, while other countries, usually the most advanced one, adopt better approaches, usually tier 2 approaches, in which more specific emission factors are adopted. For instance, emission factors not just for the nitrogen, no matter the quality of the nitrogen, but for the organic fertilizers or for specific country conditions and so on. One of the conditions that could be considered, even if it's still poorly considered, is the application of nitrification inhibitors, for instance. And this leads us to the tier 3 approaches, which I'm mentioning just because I'm giving you a brief focus on the complexity of the matter. And what do models, the so-called models, do? The models are mostly scientific tools that are meant to, let's say, study the complexity of the system without having to do measurements, to physically go in the fields and do measurements, because these are very expensive, very complex. They are done anyway at scientific level, but you cannot pretend to measure everything, because that would be simply impossible. So the models are concretely complex ecosystems that work together to take into account many conditions, for instance, the soil quality, the environmental temperature, and so on. Organic fertilizers undergo a fate similar to mineral fertilizers, so there are several processes taking place, but they do not take place at the same time. They mostly take place in a sequence. So, for instance, some processes are faster than others. The runoff and the volatilization of ammonia in particular happen very soon. And this is why application techniques affecting the volatilization rate of ammonia are likely to change what happens next, because if more ammonia goes in the air, there is less nitrogen left in the soil. An example of this is that there is scientific literature saying that injecting slurry instead of broadcasting it, so injecting it in the soil, may increase so much the nitrogen availability that nitrous emissions after ammonia volatilization are increased. And this is something that in the end does not have much practical relevance, because it is really hard to assess. Nitrous oxide emissions are really hard to predict. But for instance, in inventory importing, it is good practice to assess this as carefully as possible, because you are swapping from one form of pollution to another, and this need to be quantified. A few words on ammonia. Ammonia is quite the protagonist here, because in the end, it's the main fertilizer compound in animal slurries. And even if it's not a greenhouse gas, it leads to the production of greenhouse gases indirectly, and it is a pollutant. 92% of the ammonia pollutions in Europe comes from agriculture, and a good part of this comes from the application of animal manures to the soil, which leads us in the end to say that the best at farming level, the good practice is to reduce the early losses of nitrogen, which are mostly early ammonia losses, but also the runoff, so that most of the nitrogen stays in the soil and can be used by the crop. So target the fertilization is key. ensuring that you are not in the situation in which you have to urgently dispose of such waste. So have a sufficient buffer capacity in the manure storage if your farm, of course, is producing such effluents, and have a nutrient management plan. This is quite straightforward. And be in the position of applying such slurry when it's needed. So mostly in spring, when the temperature conditions are the best for crop growth and most of the nitrogen can be kept by the crop. And the timely incorporation of manure or slurry into the soil so that ammonia volatilization is reduced. Most of my presentation is gone. I know we are a little bit late with the timing, so I will quickly go to an example of what I mean by the complex modeling and the interplay between the components. For instance, in a livestock system, it all begins with a feed. So you can see it as a chain that begins with the feed. The feed is converted into useful products and manure that is excreted, and models follow the fate of the nitrogen that is excreted, and some is lost, for instance, at pasture level, some is lost, for instance, at barn level, storage level, until you have the final slurry or manure product that you can apply to the field. And this is also, let's say, a hotspot for losses, and that depend very much on the technique applied and the environmental conditions. So proper modeling takes all these components into account, and all the compounds, the nitrogen components, into account, because they're different. And this is done why? For instance, to model the effect of potential mitigation measures. So what we can concretely do to reduce these losses and this environmental damage. And mitigation measures can be single measures. So for instance, slurry injection alone, or seen in a combination of measures along the whole system. And for the reasons I am about to show, this is the most promising approach. We tested in different case studies in Europe, for instance, the effect of covering the slurry stores, anaerobic digestion, the high efficiency application, that is shallow injection. I'm not mentioning the what is related to mineral fertilizers, because it's not what we are talking here now. The key messages are essentially two: that the effect of mitigation measures is context specific. So as an example here, you can see that the injection of slurry has hardly any effect at the system level. So considering the greenhouse gas emissions of the whole dairy production system on the greenhouse gases, but it has a nice effect, minus 10% to minus 17% on the nitrogen losses. But there are differences between, for instance, what you can get in Eastern Europe and what you typically get in a Mediterranean system because of the climate conditions. And ammonia volatilization is of course higher under warm climate conditions. So we can advise the application of context adapted combinations, because these can lead, for instance, to mitigate the trade-offs that you can observe between greenhouse gases and nitrogen mitigation. For instance, you can see that anaerobic digestion, the acronym AD, leads to, when considered alone, to a nice reduction in greenhouse gas emissions, but even to a slight increase, plus 5% in nitrogen losses under Mediterranean conditions. But when properly considered in a system in which this is used in combination with slurry injections, slurry covers, and so on, the trade-off is completely mitigated, and you have actually a nice synergy between these measures, and you have minus 15 greenhouse gases on the footprint of the milk you produce, and minus 31 on the nitrogen losses. So the the take-home message is, when talking about these measures, to consider the whole system, and the combinations can really matter and make a difference.
Thank you, Federico. That was excellent. It's a really complicated area, isn't it? There's so much you could talk about, I'm sure. So thank you for doing that so briefly. I'm going to share slides again, and we'll move on to Francis to talk about biologically N-fixing crops.
Can you pass the slides, please, or do you want me to share the slides?
You share yours if you could, Francis. That's probably easier, isn't it? You can point
Okay,
then.
so
Yeah.
can you see my slides?
That's good. Yes, thank you, Francis.
Okay. So I will present some results about the use of legumes as a previous crops for winter oilseed rape. Fixed nitrogen can benefit the following crop, and especially winter oilseed rape, because in autumn, after a legume crop, there is a great amount of soil mineral nitrogen compared to other crops. And winter oilseed rape can uptake great amounts of nitrogen during autumn. So this crop can efficiently uptake the nitrogen left in the soil after legume crop. For this reason, we conducted 8 experiments to study the benefits of a pea crop on the following winter oilseed crop. In this figure, you can see the mean results of those 8 experiments. This figure shows the seed yield response to the nitrogen rates for the winter oilseed rape cultivated after pea. This is the green line, and also for the winter oilseed rape cultivated after a cereal crop. The benefits of a pea crop for the following winter oilseed rape is an increase in the yield when no nitrogen fertilizer was applied. The increase in yield was about half a ton per hectare for the winter oilseed rape after a pea crop compared to the rapeseed after a cereal crop. There was also a benefit, an economic benefit, because the economic optimum after a pea crop was about 40 kilo less nitrogen than for oilseed rape after a cereal crop. And there was no yield difference between those two treatments. We also investigated the use of frost-sensitive legumes for intercropping with winter oilseed rape. We conducted 14 experiments to study the effect of intercropping legumes on weed competition, insect damage, and nitrogen use efficiency. Today I will only present the results on the nitrogen use efficiency. We tested 3 legume mixtures. The first one was a mix of faba bean and lentil. The second one was grass pea, fenugreek, and lentil. And the third one was purple vetch, common vetch, and berseem clover. This figure shows the aerial nitrogen content measured in November for winter oilseed rape. For the legume, we called these legumes companion plants, and for the addition of the two. The aerial nitrogen content was measured in November because it was just before the companion plants were destroyed by frost. As you can see in the figure, there was no difference in nitrogen content of winter oilseed rape, regardless of the treatment, and the aerial nitrogen content ranged from 15 to 30 kilo of nitrogen in the companion plants. This figure shows the results of grain yield for all trials, and also for the trials where the nitrogen nutrition index was below 1, and the trials where the nitrogen nutrition index was above 1. When nitrogen nutrition index was below 1, it meant that nitrogen was limiting. The treatments were soil winter oilseed rape, receiving a nitrogen rate calculated with a decision support system. And the winter oilseed rape intercropped received 30 kilo of nitrogen less than the calculated value with the DSS. There was no decrease in seed yield in intercropped winter oilseed rape compared to soil winter oilseed rape, despite 30 kilo less nitrogen when winter oilseed rape was intercropped. There was even an increase in yield in winter oilseed rape intercropped with faba bean and lentil. And we can see that the lack of difference in yields was not the result of over-fertilization, because it was this lack of difference was also observed in experiments with limiting nitrogen. In summary, we can say that biologically fixed nitrogen by a pea crop benefits the following winter oilseed rape, because we observed the same yield and 40 kilo less fertilizer nitrogen after a pea crop. So the result is a decrease in greenhouse gas emission for winter oilseed rape, and also at the cropping system level, because there is less greenhouse gas emission in a pea crop compared to non-legume crops. Biologically fixed nitrogen by a legume companion plants benefits winter oilseed rape for 3 reasons. We observed the same yield or greater yield with 30 kilo less nitrogen, and there were fewer greenhouse gas emissions for 3 reasons. Firstly, in the companion plants, there were between 15 and 30 kilo of aerial organic nitrogen, which was less than the 30 kilo mineral nitrogen that was applied compared to the intercropped winter oilseed rape. The second reason is that the emission factors for organic nitrogen are lower than the emission factors for mineral nitrogen. And the difference also results from the greenhouse gas used for the production of mineral nitrogen. Thank you for your attention.
Thank you, Francis. That's a brilliant summary there. Thank you. I'm now going to move on to Hélène, who's going to focus on the use of cover crops. So welcome, Hélène. If you could share your slides and introduce yourself.
Yeah, I just got a technical issue and my internet crashed on my computer. So I just
no problem. If you
to talk, can someone share my slides? Sorry for that.
That's okay.
So
okay, you got it right. Okay.
I can introduce myself. So I'm Hélène Lagrange, working at Arvalis, another French institute working on crops, mainly on cereals and maize, potatoes, pasture, and linseed crops.
Hélène, are you able to put the slides onto presenter mode?
Oh, I'm trying, sorry. Can you go on slide 63 for me? And then I can do it.
I'm not.
I'm doing it.
Okay, you're doing it. Yeah, that's fine.
So we had many slides. Okay, so I think it's the good one.
That's good.
I'm going to talk about cover crops, so another agronomical level to help to not use the fertilizer. So the big question with that is what is the fertilizing effect of cover crops, and how can we estimate it to be able to use that to reduce the amount of fertilizers? So the question we have is comparing to bare soil, so case 1 on this slide, how much the cover crop can bring and how much the main crop after that can absorb. So this is the main question, and we tried to look at it in several trials. So you have here the main results that of field trials we made in France. So we worked on legumes cover crop. We had 30 trials on mixed cover crops, so legumes and non-legumes crops, 15 trials, and also on non-legumes cover crop on 24 trials. So thanks to that, we found that the amount of nitrogen in the cover crops. So you can see the results here, and of course there is more nitrogen in legumes cover crop. This is after cover crop destruction. And then the other question is, what is the fertilizing effect for the next crop? So you can see the average here, and you can see that we can have better more nitrogen for the next crops thanks to legumes and mixed cover crops. And with non-legumes, the average is 0 nitrogen available for the next crop. So the main results here are that, well, as you can see on the graph, you have a very high variability between the trials, and sometimes you have negative effects. But you can also see that when you have legumes and mixed cover crops, you often have an nitrogen effect, fertilizing effects for the next crops. So knowing that, the next question is when and how this nitrogen is available for the crop. So we made some other field trials. So you can see here on this figure many curves. These are nitrogen mineralization kinetics measured in the field. And so we learned that the percentage of nitrogen content that is in the crops and then mineralized is not the same percentage depending on the type of cover crop we have. So you have here the amount, 36% in average for legumes cover crop, 27% for mixed cover crops, and 17% for other cover crops. And we found that is dependent on the C/N ratio. And we found that the low C/N ratio gives a higher percentage of nitrogen content that is mineralized and then available for the next crop. And legumes have the lowest C/N ratio. And sometimes, so as I said, you have negative values. So it means that we think that it's because you have a temporary immobilization of nitrogen in the residues of the cover crop. And this is because microbial activity and microbial organization. So these trials help us to understand how to take into account the nitrogen effect of the cover crop and how to take it into account in the calculation of nitrogen needs for the next crop. So mostly for the winter crops, we consider that a part of the nitrogen from the cover crop is measured with soil measurements at the end of winter. And the other part is the parts used by the cover crop during the growing season. And to help farmers to use this information, we can use table, as you can see here, an example of what we use in France. We can also use modeling or measurements. And so you have in yellow here the mean amount of nitrogen bring by cover crop. From 0 to 40, 0, we consider that for non-legumes cover crop, and 40, it's mostly for legumes cover crops. And of course, it depends on cover crops types, biomass production, and the destruction period also. And you can do measurements. So we have here an example of a method that we use in France, Merci method, with measurements, and then you can use a website that gives you, thanks to the measurements, the amount of nitrogen and the amount of nitrogen available for the next crop. So I don't have so much time, so I go to the next slides. And regarding cover crops, the take-home message could be that it's important to know nitrogen effects from this kind of crops to be able to take it into account for the fertilizing effect. And so we know that legumes cover crop have the highest effect. And it's also positive to use a mixed cover crop mixed with legumes and other species. As I said, there is an effect of the C/N ratio. I did not have time to show you results, but we know also that there is an impact of the age of the cover crop, the time when it's destroyed, and the climate. And all that affects the mineralization. And so the last one is that we think that the mixed cover crops is the nicest compromise between environmental effects, because behind cover crops, we also say catch crops. The aim is to catch nitrogen during the winter to avoid nitrogen leaching. And so this can be done by the non-legumes crops mainly. And thanks to the mix between legumes and non-legumes crops, you can also have the agronomical benefits and the fertilizing effects for the next crops. So that was a quick summary for the cover crops effects. And then I know it should be the end of the meeting. I don't know if I carry on.
I think carry on. It's just really useful information. Hopefully everybody can carry on, hold on for another 10 minutes or so while we finish off. This is the last section now. So yeah, Helen, keep going, please.
Okay. So once you've done everything you can to reduce the amount of nitrogen needed by the crop, nitrogen coming from the fertilizers. Well, so we saw that you can use organic fertilizers, biological nitrogen fixing crops, and also cover crops, for example. So after doing that, you may still need synthetic fertilizers, and you can use other levers to improve their efficiency, and so to try avoid waste and greenhouse gas emissions. So I show you some results and example. You may know this 4R principles: right weight, right source, right timing, and right places. And the aim behind that is to improve crop nitrogen use efficiency. We talk a bit about the place, the right place when we talk about organic fertilizers. And I will show you here some results on right source and right timing. So regarding the timing, I show you here what we do in France for cereal crops. So we consider that it's important to know when the crop needs nitrogen, to then know when we have to bring nitrogen to the crop. And so you can see that on this graph that at the end of the winter, so we saw here it's an example for wheat. Wheat is sown in October in France, around October. And at the end of winter, this is the tillering stages. And so we can see on this graph that the crops doesn't need so much nitrogen during this period, but needs more and more nitrogen during the rapid growth between March and May, June. So the key here is to try to bring nitrogen mostly during this period, this rapid growth period. And also we found that it's very interesting to split the applications for cereal crops. This is the best strategy to be the most efficient as possible. So you have here an example of several trials we made in north of France. So in north of France, the control is 3 applications, and we tried 4 applications. And so the 0 line, it's yield results for 3 applications, and the green or red results are with 4 applications. So in north of France, you have quite high yield and high needs of nitrogen for wheat. So we can see in this condition, it is beneficial to split the spreading of nitrogen. And in average, you reach 1 quintal per hectare. It means 0.1 ton per hectare more with the splitting and the same amount of nitrogen applied. So it's very interesting to try to fit supply with crop needs. So this is regarding timing, the right timing application. And so we have some advices regarding that. And then the last application, we can also manage this one with fertilization management tools. So you have here a picture of one of them. This is an end tester. The idea is to, ask to the plant, do you need more nitrogen or not? And we can also do that with satellite images, for example. This is another way to improve nitrogen efficiency and to be the closest as possible to crop needs. And then the right sources, I show you some results of the trials we made in France to compare fertilizers type, synthetic fertilizers. So in this table, you have results of yield and protein rate on wheat trial. And for the we compared urea and nitrogen solution with ammonium. So when it's the number here is the difference with ammonium nitrate fertilization. And so we found in average that ammonium nitrate is the most efficient, very close to urea, but depending on not very close to urea, no non-significant differences regarding the yield. And the nitrogen solution is less efficient. This is the results we have in many trials in France. And then we also tried other type of fertilizers. And I show you here an example with inhibitors. We talked a bit about them. So here it's the comparison of urea and urea's inhibitor with control, and control are urea or ammonium nitrate. So you can see here the results regarding the yield and the protein content on wheat. And you can see that you have benefit to use the inhibitor. And this is thanks to its effects on volatilization. You have here results on the one trial in the graph and the mean of several trials in the table behind. So you can see that the volatilization, thanks to the use of urea's inhibitor, is very lower than the volatilization for urea alone. And so we have the same amount of volatilization than with ammonium nitrate, which is the lowest volatilization. And so you can see here the results on 6 trials that thanks to this inhibitor, it decreased the volatilization and improved the nitrogen efficiency. And then we also tried other type of inhibitors. Here it's nitrification inhibitors. So we have here 5 types of inhibitors that were tested. And you have information on the control synthetic fertilizers we use. And so you can see that there is no differences in yield and also in raised protein between the use of the control or the inhibitors, nitrification inhibitors. And as a conclusion on this use different type of fertilizers, so we can see difference in the type and difference regarding yield and regarding protein content. So regarding the efficiency, we can say that urea plus the inhibitors, urea's inhibitors, is as efficient as ammonium nitrate, very close to urea, and better than nitrogen solution. Of course, all that depends on climatic condition and soils. And regarding the nitrification inhibitors, you have no differences, but it means also that this is the same efficiency regarding yield and protein rate. But what is interesting is also to look at N2O emissions. Well, I won't go into details, but in the graph here, you have ammonium nitrate, then you have ammonium nitrate and nitrification inhibitor. Then you have urea, and then you have urea and the nitrification inhibitors. So the blue part is N2O direct emissions. And so you can see that thanks to the use of the inhibitor, you reduce N2O emissions. So that's very interesting for greenhouse gases reduction. This has no effect on agronomical results, but has high effect on greenhouse gases emissions. And that was a calculation I've done with thanks to emission factors. This was not from measurements in the field directly. So that's what I could say. I think Francis.
And you can leave that slide because
Yeah, I think you covered that, Hélène, in the previous slide. That was brilliant. There's so much information you've given us there, Hélène. It's really excellent. And all the speakers, thank you very much. You've covered a tremendous amount of information, a very broad range. What I'd like to do next is to, if you stop sharing, Hélène, and then Ben, you start the poll, because I'd like to get your views on what we should focus on next in the next webinar. You'll see that we sort of touched on a lot of topics here, and we didn't get into much detail on many of them. We just sort of glossed over a lot, didn't we? So, you know, should we look in more detail about aspects such as cover crop management, or are there completely different topics related to crops management that our theme should focus on in the next webinar? So we really welcome your guidance really on what we focus on next. Is it more detail on what we've done today, or is it a different topic entirely?
Could I ask a question? Personally, I use the N-Tester, which was mentioned, but I use it for every application and find that it gives a good feeling about how much nitrogen to apply. Is there more technology that we should be using which is relatively simplistic, because that takes into account the nitrogen in the soil, the organic manures that have been applied, as well as the artificial fertilizer? So it's a nice sum. It takes in together all those by measuring the chlorophyll level. And is there other technology like green area index that we can get from satellites to say how much nitrogen should we be applying? So it's just, the question is there technology which could simplify all of the variations that we've been talking about to give us an indication as practical farmers how much nitrogen we should be applying?
Yeah, thanks, Tony. Good question. And just to be clear for everybody else, when you talk about the N-Tester, you're talking about an instrument which clips to a leaf and measures the concentration of nitrogen in the leaf, aren't you? Like the Yara.
Yeah, I think it measures the chlorophyll content in the leaf, I think.
Yeah, it's a SPAD meter, or that sort of thing. Yeah, and that is a really good method for assessing the nitrogen status of the plant, to understand where it's deficient or not deficient. It's not that good at sort of knowing how much supply of nitrogen there is in the soil, but it will give you an indication. I mean, other speakers will comment as well, no doubt, but my view is that there are other technologies that can help as well, such as remote sensing via satellite or drone imagery to estimate the nitrogen status of a plant and whether it needs more nitrogen or not. I think they're in different levels of sort of development really, and levels of testing. The N-Tester, which you describe, is probably the most advanced of those technologies, but I think there are other tools which are sort of in the pipeline or sort of being rolled out at the moment, such as spectral reflectance measurement. But Hélène or Francis, I'm sure you've got some views too.
Yes, we use this kind of tool quite a lot in France. Well, this is for the last, we use them for the last supply of nitrogen. And we can use, like, so I said the N-Tester, but also you have different type of tools using satellite images. And as you said, the idea is to know what the crop used, as what is the nitrogen content now, and what we have to bring to reach a certain amount, which is the objectives that the tool gives. And you have different tools that estimate also nitrogen in the soil. Mostly, the more complex it is, and the more you use modelization models. Well, no, I'm not sure I'm very clear, but it's sure that you have several tools. Maybe it could be another subject for another webinar to go into this type of tool.
Yeah. Yes, it could. Yeah. Thanks, Helen.
Yes, and for oilseed crops, it's still under investigation. We are working on that, but it's not available for farmers at the moment.
Yeah. Okay, thank you. Any other questions? Okay, well, brilliant. Thank you for bearing with us. I hope you found it useful. We will get a recording link out to you in due course. Thanks very much for replying to the poll. It looks like the greatest votes are for either more detail on the end management approaches we touched on today and also soil carbon management. So that's very helpful. That will guide us as to what we do next. And thank you to all the speakers for some really brilliant slides, which were really informative. So it remains for me to wish you a good day for the rest of the day and a good weekend when it comes. And thank you for joining.
Thank you, Pete, and thank you for all of for all of you.
Thanks, Francis.
Yeah, thank you, everybody. Have a nice day.